Can you see my pointer now? Perfect. We ready to start here? All right. So, well, oh, sorry, my father's vacuuming. Let me close the door. This is going to be really noisy otherwise. There, let's make things a little quieter, shall we? All right. Hello, everyone, and welcome to the second half of my honors defense that I did from January to March, which is when the university shut down because of unforeseen circumstances. So, let's start off with some background. As you may or may not know, carbon-carbon coupling reactions are very important in organic synthesis because, well, they're like building stuff up with Legos. For example, this is the aldol reaction, which is probably one of the oldest carbon-carbon coupling reactions in the world. This is the Grignard reaction that we actually do in second year organic. And here's the Suzuki reaction, which is a very important carbon-carbon coupling reaction. But we're interested in doing it with other elements than, let's say, palladium, which is what we use in the Suzuki reaction. So our theory is, can we use bismuth to do carbon-carbon coupling reactions? Well, bismuth is fairly common. It's not very toxic. It has a big coordination sphere, and the chemistry isn't really well known at all. We know that we can make bismuth complexes that have potentially some 1,3 reactivity, because to do a carbon-carbon coupling reaction with a catalyst, you need to be able to do a 2-electron oxidative addition, and then a 2-electron reductive elimination. So a 0 to 2 cycle, 1 to 3 cycle, 2 to 4 cycle is good. A 1-electron transfer cycle does not work. So anyway, back to the topic at hand. Here is a bismuth complex that has both bismuth 1 and bismuth 3 characteristics. That was made, when was this made? In the last year, and by Marcus and Kate and Uli. And here's another interesting bismuth complex. This is the bismuth 1 complex over here, and this can actually do transfer hydrogenation using ammonia borane. Here's a generic catalytic cycle for a bismuth complex. Here comes your alkyl or aryl halide. It oxidatively adds, making a bismuth 3 species here from the bismuth 1 you started with. Then you transmetallate with, let's say, a Grignard reagent. The metal halide falls out, and you get your intermediate bismuth 3 species with both your organic fragments right over here, which reductively eliminates here to give your CC coupled product and your catalyst. The hardest part is likely going to be the oxidative addition. Now I'm going to be talking about a study that I'm currently undertaking, which will hopefully help us understand that a bit better. But for now, let's just keep on trucking. In the summer of 2019, I made a bismuth 3 PNP complex. This one right over here. I was going to try to reduce it to the bismuth 1 complex, but I didn't have a lot of success with that, because this thing tended to break down, losing bismuth metal. And we thought at the time that the problem was the bismuth nitrogen bond was simply too weak for this to work. So we thought, why not switch nitrogen with carbon? This is basically a pincer ligand, a PCP ligand that has been used by these folks down here for an iridium complex. And we figured this might work well because at the time we thought bismuth carbon bonds are very strong, because something like triphenyl bismuth is pretty stable and it's been known for years. Later on, we would learn that bismuth carbon bonds are actually not that strong, even if they're sp2 bonds. Here's what this thing will look like in theory, according to density functional theory. There's your bismuth 3 species over here, the dichloride. And here's bismuth 1 species right here. The HOMO of the bismuth 1 species is the 6p lone pair, which is this one over here. Now, the first step to making a bismuth complex is making the ligand. And the first thing I tried to do was to do benzoylic bromination on 2-bromometaxylene using N-bromocinnamide. This worked out totally fine. And then to do a Halex reaction using sodium iodide and acetone. Now, N-bromocinnamide, for those who don't know, looks like this, and it's basically a source of atomic bromine. And if you're wondering why I didn't use dibromine, the element, that's because you get this product over here if you use Br2, which is the ring attack product. Unfortunately, when I got to this here and tried to do lithium halogen exchange, I ran into some problems. Why? Well, apparently lithium halogen exchange on a dibenzyl iodide isn't very easy to do at all. Because the first halogen exchange works fine, but then this nucleophile is pretty powerful, and you have a super electrophile, the benzyl iodide, of course. So this can essentially just polymerize, which is completely undesired. And this statement just reinforces the point that I made a minute ago. So I figured, well, what if we swap the roles of nucleophile and electrophile? What about a phosphine nucleophile and the benzyl bromide electrophile? Well, as it turns out, this works out just fine. This is just an SN2 reaction between a dibenzyl bromide and diisopropyl phosphine. But the problem with diisopropyl phosphine is it's kind of expensive to buy. And the salt you get out of this reaction is very sticky and gummy. And the free phosphine, once you deprotect it here, is quite prone to oxidation, as with any trialkyl phosphine. So, I tried again to make this ligand by reducing the isopropyl chlorophosphine with lithal in ether. Now, you have to be very careful with lithal because it's quite pyrophoric, so you must handle your waste with great care. I did the same reaction as before, and again, the salt was sticky and gummy. So I thought, well, what if I could deprotonate this here in situ without isolating it and do the lithium halogen exchange? Well, that didn't quite work. Instead of getting the complex that I wanted, I just got bismuth metal falling out. So I figured, well, maybe the problem is that I can't deprotonate the salt very well. So I went ahead and got some butyllithium and decided to deprotonate the phosphine first before adding it to the dibenzyl bromide. Okay. This should have been fairly easy to isolate by removing the THF and then extracting it into any organic solvent because it's pretty greasy, right? But again, I wasn't very successful with this. At this point, I was kind of running out of diisopropyl chlorophosphine, so I figured, well, maybe I can try using diphenylchlorophosphine because I had a ton of that sitting around the lab. So, here is the reaction scheme that I ended up using, or that I thought would work quite well, to make the final product over here. Basically a reduction using lithium borohydride and THF, although as I later found out, sodium borohydride reduces diphenylchlorophosphine just as well and is actually cheaper. And this over here is basically just an SN2 reaction between these two to make the phosphine. And then this would be a lithium halogen exchange and quenched with bismuth chloride. If you're wondering why did I put the borane on, well, because the borane kind of ties up the lone pair that's on the phosphine here, and that makes it a lot harder to oxidize. And the diphenylphosphine is a stinky, volatile liquid. But this borane complex is a nice, air-stable solid that's a lot easier to handle. However, the last step has been the most troublesome, and I spent nearly all the winter trying to make it work. My first attempt was to take this immediate precursor, just do a regular lithium halogen exchange followed by quench with bismuth chloride by cooling it to -78, warming it to room temperature, and I just got black metallic precipitate and not much product. Tried using sec-butyl and methyl lithium for the lithium halogen exchange, but it wasn't very helpful. If you're wondering why didn't I use ether, well, it's because this starting material just doesn't dissolve well in ether at all. Then I tried making the Grignard out of this, but the Grignard apparently just doesn't really form very well, so I kind of gave up on that. So I figured, well, what if I metallated this using another active metal like potassium? Well, it does metallate, but the problem is that the potassium ends up going over here on the benzyl position as opposed to being on the ring where it's supposed to be. That's because the pKa of this over here is probably around 40, while the pKa of an sp2 carbon is 44. So basically you just get an intramolecular proton transfer and pop, the potassium goes over here and you've got the wrong product. We know this because the two phosphorus shifts in 31P NMR were different. And I also learned that a large reason for my struggles up here was because a bismuth carbon bond, whether it's sp2 or sp3, is rather weak and breaks homolytically very easily. In fact, if you have a dialkyl bismuth compound, you usually can't even isolate it very well at all because it will just break down into radicals in bismuth metal, and those radicals will snap together and couple. If you do that, if you have, let's say, dimethyl bismuth, that will make a large amount of ethane very quickly, and that can actually be fairly dangerous, so don't do that. So, what was the potential solution? I decided to isolate the complex at -78 degrees Celsius initially, and then warm it up to room temperature. Here's 3 NMRs of what I was doing. Here's a reaction at -78 degrees Celsius. Here's your what we think is the product over here. Here's some reaction intermediates over here, and this is some free ligand formed by that decomposition pathway I was talking about beforehand. If you warm it up to room temperature and don't hold it there for long, you get more of the desired bismuth complex and a little bit more free ligand, but it hasn't yet all broken down. However, if it sits at room temperature for any amount of time, like when I was trying to work it up by extracting the product into toluene, then you get more and more free ligand and more of the bismuth dichloride complex breaks down. I also heard that organozinc compounds give a better yield in the bismuth to carbon coupling reaction than an organolithium. So if I retry the synthesis potentially later in the summer, I might switch to an organozinc compound as opposed to an organolithium that I was using before. They're pretty easy to make. You just, I think, add zinc chloride or something like that. Yeah, to the organolithium. So, in addition to these PCP ligands, I've also been working on a CCC ligand based on an N-heterocyclic carbene. Carbenes, you've probably learned about these in Sarab's class, so they're basically like neutral carbanions. It's a carbon that's sp2 hybridized if you use hybridization. Or you basically have these two p orbitals are involved in bonding. This p orbital over here has a lone pair on it, and there's an empty p orbital sticking up here. Sorry, I mean there's actually one the s orbital. Sure, sorry, I mean one of the s orbitals here is busy bonding. Then one of the p orbitals is also bonding. One holds a lone pair, and the last one's vacant. That's why carbines can be pi acceptors. So my theory on how to make a complex, which is this one over here, was to start with imidazole, turn into benzylimidazole via a basic SN2 reaction, do another SN2 reaction on the dibenzyl bromide, and then remove the bromides, replacing them with triflates using silver triflate and acetonitrile, deprotonation, lithium halogen exchange here, and quench with bismuth chloride. I also was thinking about trying to do this with TMS group here inside of the benzyl group, but I couldn't get a single clean product, so I kind of gave that up in a hurry. This is what TMS imidazole looks like, by the way, if you've never seen it. And the base, LiHMDS, looks like this. It's a good base because it's strong, but it's very bulky, and so it doesn't act as a nucleophile when you don't want it to. So I meant that was supposed to be an anion exchange, by the way. Sorry about that. Basically, the thing is, the complex I was showing before, or the dibromide salt, it's dicationic salt, which is soluble in something like methanol, but LiHMDS and methanol don't go well together. So, one solution is to replace the strongly coordinating bromines with more weakly coordinating anions, such as triflate. How this works is basically the silver triflate dissolves in acetonitrile, and then it takes the bromide, and the silver reacts with it and crashes it out as silver bromide. And because the silver bromide is so insoluble in just about anything, the reaction goes to essentially completion. And this is the structure of triflate over here, in case you're wondering. Now, unfortunately though, this reaction wasn't as high yielding as I hoped. So I might try it with trimethylsilyl triflate at some point, because trimethylsilyl triflate just makes trimethylsilyl bromide as a byproduct, and that's volatile and easier to remove. So, plan for the future, whatever that is. Finally, I did a DFT study on all these three complexes. 1A is the isopropyl PCP complex. 1B is the diphenyl PCP complex, and this is the one based on a carbene. As you can see, the dialkyl phosphine is kind of in the middle with the energy of the HOMO. The diaryl phosphine's HOMO is the lowest in energy, and the N-heterocyclic carbene has the highest energy HOMO. Why is this useful? Well, because oxidative addition, as I said before, is probably the most challenging step of any bismuth catalytic cycle. And the higher the energy of the HOMO, the more facile that step should be. And this is not unexpected because a carbene is a much stronger electron donor than a phosphine, and so the energy of the HOMO should be higher. So, the last thing I did throughout the winter was making a PNP bismuth complex. I made this complex over here in the summer of 2019, back when the world was young and there was no COVID threat. It's fairly easy to make, but as I said before, I didn't have much success in reducing it. And when Kate tried to make crystals of this, it just made low quality crystals that weren't very good for XRD. And this one here also doesn't really dissolve in much other than halogenated solvents. And kind of into ether in THF, but still, I would like this to go into something like hexane if I could. So I decided, well, let's replace those methyls with terp-butyl groups on the backbone. Should also be easy to make, right? Probably won't be any easier to reduce, but if you keep trying hard enough, I imagine you'll be successful sooner or later, no? And T-butyl groups might help to make it crystallize a little better, and it should be a little more soluble, at least in theory. So, how do I make PNP complexes like this? The first step is just aromatic bromination using bromine and acetic acid. Then you triply lithiate this thing over here, quench it with 2 equivalents of diisopropyl chlorophosphine. You have to add 3 equivalents of butyl lithium because the first equivalent just deprotonates this. Then you can deprotonate the NH again here in pentane and crash out the salt here, which you can easily which you can then react in ether with bismuth chloride to make your PNP, sorry, bismuth dichloride complex. And here's basically the annotations for what I was just talking about. Aside from my being able to actually make it, this complex has a very interesting feature when you look at it by NMR. Okay, here's the phosphorus NMR. Nothing special about that. Is there? Well, okay, we have the complex. The shift is minus 11.49, which is up here for the free ligand, which is kind of expected because of the bismuth being a big atom, and big atoms on phosphines tend to move the chemical shifts downfield, which is this way, to left. But here's where the NMR gets really interesting. The aromatic region looks kind of normal. A little bit of DCM over here. But see this isopropyl peak, the methine protons on there. They're hardly above the baseline. You gotta zoom way in to see them, and they're in an extremely broad and very short. Also note how broad the peak is for the CH3 groups on the isopropyl. Now you might think, okay, this is just a spectrometer shimming problem, but look, the T-butyl peak is nice and sharp. So what is happening here? Well, okay, here's all the annotations for what's what, in case you don't remember, or in case I forgot to tell you. Well, the theory that I have is that we have a bouncy bismuth. At room temperature, the bismuth dichloride interconverts between these two forms very quickly. So the bismuth is only ever bonded to one phosphine at a time. And how do we know that? Well, if you run VT-NMR on this complex, which is very similar, the phosphorus shifts over here become broader and broader, and eventually they split into 2 separate peaks. So what kind of catalysis could we do with bismuth? Well, the bismuth-carbon bond is rather weak. This makes bismuth-carbon complexes hard to make, but weaker bonds are also easier to break in a catalytic cycle. And these folks over here were able to use a bismuth 3 compound right over here in order to do a carbon-carbon sp2 biphenyl coupling reaction. Granted, this was not catalytic, but hey, this is definitely a start. The intermediate here is this bismuth aryl fluoride compound, and the reason why this reaction works is because the bismuth carbon bond right over here is pretty weak, so it can easily rearrange to react with the phenol over here in the ortho position. The bismuth doesn't fall off the ligand here because it's a chelating ligand. So chelating ligands are in general pretty important with bismuth, otherwise it'll just fall off. So here's some people I'd like to acknowledge, including Nick Roberts, Nick Murphy, and Junie Liu for technical assistance. That means glassware cleaning. Kate Marzenko for X-ray crystallography. It's Rob for being the honors thesis supervisor. And Marcus for continuing to work on the PNP complex I made in the summer. And for working on a similar PCP ligand that was had T-butyl groups as opposed to isopropyl groups. So this is the end here. You folks, sure. No, I'll go to slide 11. Yeah, there. I don't think it's the problem with the lithiation. I think the problem is more likely that the complex formed okay, so the bismuth got here, but then when it warmed up, it broke down again. Yeah, basically the same problem. I started at minus 78 degrees and let warm to room temperature for both the lithium halogen exchange and the bismuth chloride quench. It is. I tried running them for both an hour and running them overnight, and it didn't really seem to help either way. I think the problem is the complex isn't super stable. We even tried adding Tamita to it, but that didn't really help much. I'm also thinking maybe if the phosphine was a better donor or something, it could potentially make the date of interaction a bit stronger. Hmm. Yeah. I also missed something here. You have to actually do the deep protection at after this here with refluxing triethylamine. Sorry, I forgot to add it. But yeah, I'm wondering too, maybe you could use trips or something like that, or mesotylphosphine or something like that. That might make it a little more stable. Because if you have a bulky phosphine, it might trap the bismuth in there. Even if it's thermodynamically unstable, it might be such a large kinetic barrier that it can't fly off. Will do.